Hello there and welcome to this series of videos going through the content of A-Level Further Maths. Here we're looking at loci on an Argand diagram so we can answer questions from exercise 2e. This is the first part of two videos. In the first video we're going to look at the basic diagrams that you could be asked to construct in this chapter, and in the second part of this video we're going to look at how they can involve some problems, finding maximum, minimums, regions of arguments, etc, to go on top of what we're learning in this video. So here is just the basics of how you can construct loci diagrams given certain algebraic rules to do with complex numbers. So in this case here, a nice simple example is we've got to sketch all of the coordinates, all of the complex numbers, we'll call them z, that has a modulus of 3. Now remember, the modulus 3 represents the distance from the centre to the complex number has a distance of 3. And if we think about it, a circle provides that property where the distance to the centre around any point around that object has a distance of 3. So what we're going to get is a circle that looks roughly like this. Now any complex number that you have that's along this circle here will have a distance of 3. And that's what it means to have a modulus z of 3. Okay, so that's what we mean by finding loci. All of these points that are along this line form the locus of points that has a modulus of 3. Each one of these complex numbers that surround this circle all have a modulus 3, or in other words, they all have a distance from the centre of a value 3. Okay, so that's what we mean by sketch the locus of z, where the modulus of z is equal to 3. Okay, and we could be asked to move this circle around as well. So for example, what will this locus of points look like? The modulus of z minus 4 is equal to 5. And we're going to be asked a couple of questions on this sort of diagram here. So when we see the modulus of z minus 4, here think of this as like a graph transformation. When we take away 4 from inside the brackets, we're actually going to move the diagram to the right by 4, and then it will be a circle of radius 5. You could effectively think of this as what complex numbers, once we've subtracted 4 from that complex number, will give us a radius of 5. You could think of this, maybe z could be just the real number 9. 9 minus 4 gives you 5, and then it will be the modulus of that 5, which will give you 5. Z could also be minus 1, so we've got 9 minus 1 could also be a number here. Minus 1, take away another 4, gives us minus 5, and the modulus of minus 5 is 5. Okay, so it's going to be a circle with radius 5 around a centre of 4, 0. So in other words, we could think of this as a problem of plots the complex numbers that after there has been a subtraction of 4 have a radius 5. And the centre of this circle here is going to be at 4, 0. Think of this as like a graph transformation. It's going to move right by 4. A good question would be, well, how does it move up and down? Well, if this was an I here, then it would move up by 4 because the vertical axis here is the complex, is imaginary dimension, and this one here is the real dimension. 4 is a real number. Okay, so this is what the diagram here looks like. So let's go ahead and answer these subpart questions. Find the values of z such that the imaginary part is equal to 0. Well, if the imaginary part is equal to 0, it's going to be these two complex numbers here. The imaginary part needs to be equal to 0, and if it has a radius 5, then it's going to go out to coordinates of minus 1 and 9, just like we mentioned earlier. A slightly more difficult problem would be find the intersection of points where the modulus of z minus 4 equals 5, and the real axis, where the real axis equals 0, intersects. Now, when the real part's equal to 0, that effectively means it's a purely imaginary number. So we're going to get these two coordinates here. Now, how might we find out those coordinates? Well, we know the distance is 5 along here. We know that the distance along here is going to be 4. So you could think of this as a kind of Pythagoras-based problem. So you could think of it like that. Or you could think of it from the point of view of the circle here will have an equation of x minus 4 squared plus y squared equals 25. And you will have seen that from the A-level maths module in which you study circles. What we're going to do here is substitute in x equals 0 because we're working along the y-axis, and find out the values for y, and it's going to be plus or minus 3. And we'd get exactly the same answer here, you can see, if we were doing this by Pythagoras' theorem as well. 5 squared minus 4 squared is 3 squared, so the answer here is 3 plus or minus 3 down below. So we have two coordinates here. We're going to have 3 and minus 3 down here, but remember it's on the imaginary axis, so we're going to get 3i or minus 3i. Okay, so this is how we sketch some locus of points to do with complex numbers. Here's some pretty simple problem solving that you can expect to see following a question like this. Okay, what about this problem here then? Z minus 5 minus 3i equals 3. How do we sketch that set of locus points? Well, in this case here, remember, think of it as graph transformations. It's going to be moved minus 5, so that means it's going to be moved right by 5. And when it's a minus 3i, this means that it's going to move up by 3. So that's going to find us the centre of the circle, and then the circle is going to have a radius of 3. So each of these parts correspond to where the circle is going to have a centre, and then this 3 at the end here is the radius. So we can think of this as a circle with a centre at 5, 3, with a radius equal to 3. So just like this. And when you're drawing these sorts of circles out, be really careful whether you consider that it's going to cross the y-axis or not, whether it's going to cross the x-axis or not. And in this case here, because they're both 3, it goes 3 up and the radius is 3, we know that it's going to touch the x-axis but not go through it at 2 points. Okay. Alright then, so we can think of any complex number that's on the circumference of this circle. Once we've subtracted 5 and subtracted 3i, will then give us a radius of 3, or a modulus of 3. Okay. Alright, so we've looked at circles that can be formed by using the modulus symbol. In this case here, we're going to increase the level of difficulty of the problem a little bit more by considering moduluses on both sides of an equation. So the modulus of z, or in other words, the distance to the point 0, 0, is equal to the distance to the point 6i, or z minus 6i modulus. Always think of modulus as distance. That is a very good piece of advice there. Modulus is basically equal to distance when you consider the locus of points. Okay, so the modulus of z represents the distance of a complex number point from the 0, 0 origin. Z minus 6i considers the distance of the complex number from a fixed point of 0, 6, and the distances between these two coordinates effectively must be equal to each other. So what we effectively have got here is the point 0, 0, the point 0, 6, and then a perpendicular bisector that will cross through both of the points here at an equal distance. Take any point along this line, the distance to each of the complex numbers or the starting points is going to be equal, and that's what the question is looking for. The distance between the point 0, 0 and the distance between the point 0, 6 must be equal, so it's a perpendicular bisector here. Effectively, the equation of this line is y equals 3, or effectively z equals 3i. Okay. Alright, so how can we show this using an algebraic method this time? Well, what we can do here is, if we think about z as the number x plus yi, or any imaginary number here, we've got the modulus of x plus yi equals the modulus of x plus yi minus 6i. Now remember the definition of the modulus symbol, it's the square root of the real part squared add the imaginary part squared. So what we're going to do first is group together the imaginary parts on the right hand side of the equation and then follow the instruction of the modulus symbol. And the modulus symbol gives us the square roots of x squared, the real part squared, plus the imaginary part squared. That's the definition of modulus. And this is going to equal the real part squared add the imaginary part squared. And what's different on the right hand side is that the imaginary part is y minus 6 squared. And now we just need to solve this equation. Hopefully we get an answer of y equals 3. So square both sides, expand the brackets on the right, cancel out where possible, and then rearrange this equation, and we get y equals 3, just like we'd expect from seeing the page before where we had a horizontal line at the value 3. Y equals 3 is the equation of the locus of points for this piece of algebra. Okay. Alright, moving on to questions without a modulus symbol. Let's look at the argument type questions now. And what this wants you to do is plot all of the points where the argument for z is equal to pi by 4. So all of the points that we're about to plot must have an argument of pi by 4. Now remember, pi by 4 is like 45 degrees. Okay. And it's from the point 0, 0 because we haven't transformed the z complex number yet. Later on it will get more difficult when we have to transform this complex number z. So what it's going to be is it's going to form a line where each of these complex numbers have an argument of pi by 4. The distance or the value of rotation round from the real positive axis here is going to be pi by 4. We call this a half line because it's not a full line that will carry on downwards, it's just a half line that stops at the point 0, 0. This is effectively where the line starts. Why does it start here? Well, because we haven't transformed the z in any way in this question. It's just this half line that appears here, starting at 0, 0. Alright then, so how can we now find the equation of this line? The question is, then find the Cartesian equation of the locus algebraically. Well, how are we going to do this? Well, the way that we work out the argument is to use the tan value, isn't it? So it's tan of the imaginary part over the real part in this case. So it's tan minus 1 of y over x. Tan minus 1 of y over x. Now to solve this equation, we're going to need to tan both sides to get y over x equals tan pi over 4. We can work out tan pi over 4. Tan of 45 degrees is 1. So substitute that in and then times the other side by x, and we clearly get y equals x, which is exactly what we'd expect this line here to be. We need to restrict the domain slightly. X is greater than or equal to 0. It's not in the negative quadrant at all. Okay. Alright then, so let's have a go at this one here. Now then, the argument of z minus 2 equals pi by 3. Now the only way in this will change the question here is now that just like a graph transformation, we'll move this right by 2. Our starting point for our half line is now going to be at the point 2, 0. The value of rotation round from the real positive axis is going to be pi by 3, so a bit more than before, a 60-degree angle round from here to here, pi by 6. Okay, but it's going to start at 2, 0 because we've applied effectively a transformation, a complex transformation of subtract 2 onto this complex number here. Okay, alright, so that's the answer to this question here. How do we then find the equation of this line algebraically? Well, very similar to before. Replace z with x plus yi. Group your real parts and your imaginary parts together, because the distance along this line here, if we have this coordinate here, is going to be x. This is the coordinate xy, but the distance along from here to here is only x minus 2 because we've cut out a portion of 2 off of the real axis here. So it's x minus 2 along the bottom here. The real part is still y. So the imaginary part is still y, so it's tan minus 1 of y over x minus 2 equals pi by 3. Tan both sides. Work out what tan of pi by 3 is. I think that's the square root of 3. And then times x minus 2 onto both sides. And we get the equation of the line y equals root 3x minus 2 root 3. Okay. Now, how do we get it to start up here, for example, at 5i? Well, all you'd have to do here is do arg of z minus 5i equals pi by 3, for example, and that will start it up here at an angle of pi by 3. And it will be at an angle when you draw in a horizontal of pi by 3 like this. Okay. Alright then, so another challenging one here. Arg of z plus 3 plus 2i equals 3 pi by 4. Now if we think of this as a graph transformation, this is actually going to move our starting point to left 3, and then it's going to move it down 2, because inside the brackets is effectively opposite. We need to find the complex number that when we add 3 and add 2i onto it, gives us an argument of 3 pi by 4. So it's left by 3 and down by 2 for this type of graph transformation or complex transformation. So we're going to start the line at left by 3, down by 2, and the angle is going to be at 3 pi by 4 from this horizontal. So it's round 3 pi by 4. Just like this. This is the angle of 3 pi by 4. If the angle was negative, then you'd obviously have your line on the bottom side of the horizontal line. Okay, so the line is this half line here, just like we've got there. Okay, and once again it's looking for us to use an algebraic method to find the equation of the line, so let's go ahead and do that. So it's going to be substituting x plus yi, group together all of your imaginary and real parts, and then apply tan minus 1. Now let's draw out the triangle that we're working with here. It's going to be x plus 3 in this case here. This is the point xy. Okay, so the coordinate here is xy, but the distance along this triangle here is going to be x plus 3. X plus 3, and this distance, height here, is going to be y plus 2. Okay, so now let's apply the tan of 3 pi by 4 here. Tan of 3 pi by 4 is minus 1 times by x plus 3. Take away your 2, and we'll get y equals minus x minus 5. Okay, so that's how we'd work out the equation of that. We have to limit the domain as well, so it's only when x is less than minus 3. Okay, don't forget to put that bit in there. Okay, Right, so your turn to have a go at plotting some complex loci. Pause the video and have a go at this one. Alright then, so let's have a go at this together. Then the first one here is a bit of a basic one. It's not left, it's going to be down because it's an I value. So it's down 3 and it has a radius of 3. Now why is it down by 3? Because it's plus 3i. So whenever there's an I part on this transformation, that means you're moving along the imaginary axis up and down. And it's always the opposite of what you've got inside this transformation. So it's up 3, how it looks on here, but in fact it's opposite, it's down 3. So we're going to start, we're going to have the centre of the circle at 0 minus 3 and a radius of 3, so it's going to exactly intersect the point 0, 0. So it's going to look exactly like this. It's going to intersect down here at 0 minus 6, and it's also going to intersect here at 0, 0. It's a good idea. If you can quickly calculate the points at which it intersects the axes, then you write them on. Okay. The next one here, question 6. Now this is a different one. It's not going to be a circle, this one here. It's going to be a perpendicular bisector between the points 6, 0 and 2, 0. So it's going to be the equal distance from the point 6, 0 to the point 2, 0. So this is going to cross through the coordinates of 4 and then some y value. So we've got a x first coordinate here at 6, 0, second coordinate here at 2, 0, and it's going to cross through this line here. This line where x equals 4 is the line at which any point along this line there will be an equal distance between the 2 points. So it's always going to be an equal distance. That's what the modular symbol means. It's looking for distance. Here the distance is 3 from this point. Here the distance is equal from these 2 points. Okay. Question 9 here is a little bit tricky. Unless you've seen the trick, it is very difficult to get this one. Now what I'm going to do, inside the brackets, I'm going to factor out minus 1. So that will give me z minus 2. And then I'm going to use the rule that for moduluses, you can times the moduluses together separately. Now here, what's the modulus of minus 1? What's the distance from the centre of 0 to the point minus 1? That's a distance of 1. So effectively it's 1 times the modulus of z minus 2, which is just going to be equal to 3. So now this is turned from a difficult problem into quite an easy problem. It's right by 2 for the centre of the circle, and it's going to have a radius of 3. So the centre of the circle is going to be at 2, 0, with a centre with a radius of 3. So this point here is going to be minus 1, 0, and this point here is going to be at 5, 0. Okay. And the last one here is an argument-based question. Now, where are we going to start the half line? It's going to be at minus 2, the opposite of this transformation here. So minus 2, minus 2. And it's going to have an argument of minus pi by 4. Now, what I would suggest you do is draw in that horizontal line that we're measuring from, and then it's going to be down, because it's a negative value, down by a turn of pi by 4, and then we'll draw in that half line there. So it's a strictly diagonal line down here. The equation of the line is going to be y equals minus x minus 4. Just because, and the reason I know that so quickly is because pi by 4 is at a 45-degree angle. However much you move right by, you're going to move down by that same amount. It's going to have a gradient of minus 1 effectively. So if I've moved across by 2, I move down by 2. So I know my intersection is going to be at minus 4. So that's how I know so quickly that the equation of line equals this. And of course we must remember to put on the domain where x is bigger than minus 2. Alright then, so that's a very quick look at some of the questions from exercise 2E. Just have a go at the basic ones before we go on to the problem solving elements of this chapter. Make sure you have lots of practice so that when we come to solve some problems, you're well versed in how to construct loci diagrams very quickly. We've got three types. We've got circles, we've got perpendicular bisectors, and we've got half lines that are formed by the arguments. Alright then, thanks very much for watching this video.